Bismillahirrahmanirrahim. In this lecture, we will do some exercises related with elementary row operations and echelon forms. As is first exercise, write the given matrix into row echelon form by using following elementary row operations. Here is first operation, symbolically P. So P means permutation, 1 and 2, row number 1 with row number 2. So it means permute row number 1 with 2, or in other words you may say exchange row number 1 with row number 2. Second operation, we have to add row number 1 to row number 2, but before adding you have to multiply row number 1 by minus 2. So if you multiply by minus 2, the answer is added to row number 2 in order to make row number 2 become 0. Row number 2 first element become equal to 0. Similarly, A134 means addition. First you multiply row number 1 by 4 and add it to row number 3 in order to make first element of third row equals to 0. Similarly, A14 minus 2 means add. First you multiply row number 1 by minus 2 and then add it to row number 4 in order to get the 0 element of the first element of the fourth row. In third operation, we multiply row number 3 by minus 1, row number 3 by minus 1 and row number add it to row number 2. Similarly, in fourth operation, we have to add row number 2, multiply row number 2 by minus 2 and add it to row number 3. Similarly, row number 2, we multiply row number 2 by minus 2 and add it to row number 4. In operation number 5, multiply row number 3 by 1 over 13 and in 6, multiply row number 3 by minus 9 and add it to row number 4. So after applying these operations, we may obtain the echelon form. What is the advantage of echelon form? Let us suppose that matrix is adjoint matrix, and after application of these six operations, we may obtain echelon form. By using that echelon form, we may obtain the solution set for that augmented matrix. In detail, we see here, as you apply the first operation, that is permutation of 1 to 1. So here you see, which is just change row number 1 by row number 2. So after changing, you see the matrix become 1 minus 1 2 1 2 1 minus 1 3 minus 4 6 minus 7 1 2 0 1 3. So now our new matrix is, after applying first row operation, 1 minus 1 2 1 2 1 minus 1 3 minus 4 6 minus 7 1 2 0 1 3. Now in order to make last three rows 0, or in other words, in place of we want to write in place of 2 0, in place of minus 4 equal to 0, in place of 2 equal to 0, in order to make echelon form. So we have to apply here addition operation, multiply row number 1 to minus 2, row number 1 to minus 2 and add it to row number 2. So you will obtain 0 here. Similarly, add row number 1, multiply by 4 and add it to row number 3. So we obtain 0 here. Similarly, multiply row number 1 by 4. The answer is 4 minus 1 8 1 and add it to row number 4. So we obtain 0 2 minus 3 1. So third step, put the leading one in the set 2, 2 position. So here you see, the 2, 2 position, the element value is 3. So now we want to make 3 equal to 1. We want to change 3 equals to 1. So we have only 3 operations. One is called addition, second is multiplication, and third is permutation. These are 3 legal operations you may apply here. Nothing else operations you may. So first, in order to make 1 in place of 3, we just add, we just want to make 3. So we multiply, we could accomplish this by multiplying row 2 by 1 over 3. However, this would introduce fractions into the matrix and thereby complicate the remaining computation. In hand calculation, pure algebraic error result if you avoid the use of fraction. So in order to avoid the use of fractions, we must apply here the addition operation again. First we multiply row number 3 by minus 1 and add it to row number 2. So we will obtain 0, 1, minus 6, minus 4. So now 1 is the key element of the second row, and below that 1 we want to make 0, 0 in order to find out the echelon form. Now using using that key element, we want to change 3, 3 position equals to 1. So we multiply row number 3 by 1 over 13. We find out 1 here. Use the leading 1, 3, 3, 1 position to put zeros beneath it in column 3. The appropriate row operation is to add minus 9 times row 3 to row number 4. Now you see that matrix, you know, is echelon form. And here you see since it satisfies all the condition of echelon form, all columns having leading ones. Okay. Second condition, below all leading ones, all elements are 0 here, right? And or if complete entirely 0 rows is on the bottom line. So it satisfies all the conditions. It means now that form is called echelon form. It is echelon form. Next example. Determine the reduced echelon form of matrix A. Here you see matrix A is 3, minus 1, 22, minus 1, 5, 2, 2, 4, 24. So again we have first start with from the beginning matrix, that is 3, minus 1, 2, minus 1, 5, 4, 22, 2, 24. First we apply here addition operation in order to find out the key element 1 at row number 1. We first add the addition operation. First we multiply row number 2 by 2 and add it to row number 1. So we will obtain, after applying that addition operation, we will obtain that matrix. That matrix is 1, 9, 26, minus 1, 5, 2, 2, 4, 20. So you see at position 1, 1 we find out the key element. Since we have only 3 operations, by using these 3 operations we may apply here. Apply here. Okay. So secondly, again in order to get the zeros behind 1, we apply here the addition operation 2 times. First we multiply row number 1 by 1 and add it to row number 2. We may obtain 0, 14, 28. Again we multiply row number 1 by minus 2 and add it to row number 3. So you will obtain 0, minus 14, minus 28. Right? Now second 2, 2. Now we want to find out at 2, 2 position of the matrix key element. So how may we find the key element at 2, 2 position? Just by using the multiply operation. Here you see the third operation is multiply row number 2 by 1 upon 14. So after multiplying row number 2 by 1 upon 14, we may obtain 0, 1, 2. Now in operation number 14, in order to make minus 14 equal to 0, We again apply here the addition operation in order to make minus 14 equal to 0. First we multiply row number 2 by 14 and add it to row number 3 and in order to get 0 zeros. So we apply here two addition operation. Finally we obtain that matrix 1 0 8 0 1 2 0 0 0. So that form is called echelon form since it's satisfying all the condition of raw echelon form. So here is one of the important concept in echelon form, that is called the rank of the matrix. What is rank of the matrix definition? The number of non-zero rows in any raw echelon form of matrix is called the rank of the matrix. It is important since it may be applied to find out the eigenvalues, eigenvectors, or it may be find out to know the consistency, whether the system is consistent or not consistent, since it's also apply to find out the stability, instability of the system. So here is the exercise. Find the rank of the matrix A. So here the given matrix A is 3 1 4, second row is 4 3 5, third row is 2 minus 1 3. So if you apply addition in order to make the key element first one at row number 1, column number 1 position, we want to find out the key element 1 here. In order to get key element at first 1 comma 1 position, now here you see the value at 1 comma 1 position is 3. We want to make 3 into 1, but we have only 3 valid operations. One is called addition, second is called permutation, third is called multiplication. If you apply here the addition operation in order to get in order to get a key element at one or reading 1 at 1 comma 1 position, so we have to multiply row number 3 by minus 1 and add it to row number 1. So you see, if you multiply row number 3 by minus 1, we may obtain minus 2 plus 1 minus 3. So 3 minus 2 equivalent to 1, 2 plus 1 equal to 3, 1 plus 1 equal to 2, 4 minus 3 equal to 1. So now our next change row after applying addition operation, our change row is 1 to 1. Row number 1 is now, you see, row number 1 is now 1 to 1. So in order to get zeros behind key element 1, we apply here two addition operation. First we have to multiply row number 1 by minus 4 and add it to row number 2. So if you multiply row number 1 by minus 4, we obtain minus 4 minus 8 minus 4. So if you add 4 minus 4, so answer is 0. Similarly, 8 minus 8 plus 3 equals to minus 5. Similarly, minus 4 plus 5 equals to 1. So our now we have changed second row. Change second row is 0 minus 5 1. Again we apply here the addition operation. First we multiply row number 1 by minus 2 and add it to row number 3. So after applying addition operation to row number 1, you may obtain minus 2 minus 4 minus 2 and add it to row number 3. So minus 2 plus 2 equal to 0, minus 4 minus 1 equal to minus 5, minus 2 plus 3 equal to 1. So our change matrix is 1 2 1, 0 minus 5 1, 0 minus 5 1. So in order to get the key element now in the 2 comma 2 positions or second row second column position, we must apply here multiplication. So if we divide row number 2 by minus 5, the answer is 0 1 minus 1 upon 5. Now by using second row we may find out the third row. So if we multiply row number 2 by 5, the answer is 0 5 minus 1, and add it to third row, the answer is 0 0 0. So you see now second our echelon form, that is reduced echelon form, is 1 2 1 0 1 minus 1 upon 5 0 0 0. So you know how many non-zero rows here. So here we have only two non-zero rows. That is, first row is non-zero row, second row is non-zero row, and third row is completely zero rows. So what should be the rank? So you know the rank is 2 for that matrix. So in that way we may find we have to convert any matrix in echelon form, reduced echelon form, and then find out how many number of rows there. If the number of rows, non-zero rows here is 2, so the rank of the matrix is 2. Next exercise, determine whether the following matrices are raw reduced echelon form or reduced echelon form or neither. So you see first example is 1 0 minus 1 0, the first row of that matrix. Second row of matrix is 0 0 1 2. Third row of the matrix is 0 0 0. So since it's satisfying all the conditions of REF, reduced echelon form, but not it's satisfying REF, so we may say that that matrix is that matrix is in reduced echelon form. Why we may say? Since all rows have first row is the leading one at the first position, second row is also have the leading one, and below leading one all elements are 0, and on the consecutive row, second row, third row, the leading one on the right side of the first row, and entirely zeros are on the third row. So that means it's satisfying the condition of REF. So that matrix is in reduced echelon form. Second example is on the second column of the first row is 1025 1002 0110. So you see there must exist leading ones on each row. So if you analyze row number 1, so at first row, first column position, there exists leading one. On second row, there exists leading one. And on third row, there exists leading one. So since it satisfies the first condition. But the second condition is that below leading one, all elements are 0. So on first row leading one, below that leading one, there does not exist entire zeros column. So we may say it does not satisfy the condition of reduced echelon form or RREF. So you may say it is neither. It is not in reduced raw echelon form, or it is not in reduced echelon form. Third example. So this is third example is the matrix is first row of that matrix is 1 0 0 0. Second row of the matrix is 0 0 0 1. So if you analyze the four conditions, first condition is each and every row must have the leading one to satisfy that condition. That's good. First row is leading one, the first full column and first row. Second row has the leading one at last column of the second row. So both rows have the leading one here. It also satisfying the second condition, below leading one all elements are 0. And on the consecutive row, first and second row, the leading one on the second row is on the right side of the first row. What does it mean? It means it is in the form of RREF, reduced raw echelon form. Why you say it is raw reduced echelon form? Because on the leading one column, except one or other elements on that column must be equal to 0. You see, in first column position, the leading one is 1, and below is 0, nothing else element. And on the second row, the leading one there is 1 on the second row, fourth position, and above 1 is also 0. So you may say it is in reduced raw echelon form. Now the fourth example here, fourth example is in fourth example we must first analyze whether it is reduced raw echelon form or reduced echelon form or neither. So if you check, the first row has the leading one, second row is also on the leading one. Second condition, below leading one all elements are 0, yes, leading one all elements 0. Third condition, the consecutive rows or second row leading one must be on the right side of the leading row of the first row position. But here you see the leading one of the second row is on the left side of the leading one of the first row. It means it is neither raw reduced echelon form, it is not reduced form, or neither, since it does not satisfy the third condition. Now our fifth example is first row is 0 1 0 0, second row is 0 0 1 0, third row is 0 0 0 0. So since check whether it satisfies conditions of raw reduced form or not, or RREF. So analyze it. First row has the leading one, second row is the leading one, and entire rows are on the bottom line. And below leading one all elements are 0, or above leading one are 0. So here see the leading one on one, first row, second column, the leading one is 1, and below all elements are 0 here. On the second row, the leading one is on the position of second row, third column, right? So above and below all elements are 0 except leading one, and third row is entirely of 0. So since it satisfies all the conditions of raw reduced echelon form, so we may say it is in RREF form. Now the last example here, 1100. So since it's also satisfying all the four conditions, so you may say it is reduced echelon form, or you may say it is also in RREF form. Next exercise. Using elementary row operation, we want to find out the solution for this equation, system of three equations. Here in that system of equations, we have three equations and four variables, and we are interested in to find the values of four variables by using elementary row operations. So first we write that matrix in augmented matrix form. So that matrix augmented form is 1 1 minus 1 1 1 2 3 1 0 4 3 5 3 minus 1 5. So that matrix now is in the form called augmented matrix form. Now in order to convert it into echelon form, we have to apply here the addition operation. First we multiply row number 1 by minus 2 and add it to row number 2. So after multiply row number 1 by minus 2, we may obtain minus 2 plus 2 minus 2 minus 2 and add it to row number 2. So minus 2 plus 2 0, minus 2 plus 3 1, plus 2 plus 2 plus 1 3, minus 1 minus 2 plus 0 minus 2, minus 2 plus 4 2. So our change row is 0 1 3 minus 2 2. So you see now we have in second row we already have the key element. So by using that key element we want to change change the value below the key element equals to 0 in order to get the echelon form. So we must apply here the addition operation. Must multiply row number 2 by minus 2 and add it to row number 3. So if you multiply row number 2 by minus 2, you have 0, minus 2, minus 6, plus 4, minus 4. So if you add it to row number 2, row number 3, so you'll obtain 0, 0, 0, minus 2. Not so simple system. Here we have system of equations x1 plus 3x2 minus 2x3 plus 2x5 equal to 0. 2x1 plus 6x2 minus 5x3 minus 2x4 plus 4x5 minus 3x6 equal to minus 1. 5x3 plus 10x4 plus 15x6 equal to 5. 2x1 plus 6x2 plus 8x4 plus 4x5 plus 18x6 equal to. So here you see how many variables. There are 6 variables. And how many equations we have? We have only 4 equations here. And we are interested in to convert that matrix into reduced echelon form. We have only 3 valid elementary row operations. First is called addition, second is called permutation, and third is the multiplication. So first we write that system of equation in form of augmented matrix. So here you see it is our augmented matrix first. We have to apply here which operation in order to get zeros behind 1. We have to apply here the addition operation 2 times to get zeros behind 1. So after severally applying elementary row operation, we found reduced row echelon form, where last row is entirely of zeros. So you see in first position, 1 comma 1 position, there exists 1, and in second row, third position, or you may say 2 comma 3, at 2 comma 3 position we have leading 1, and in third row leading 1 is on the position is row number 3 and column number 5, 6, column number 6. So that leading ones showing showing the position of the variables, position of the variable x1, position of the variable x3, position of the variable x6. But what's about remaining variables that are x2, that is x3, x4, and x5? So these variables, you may say, are called free variables, and because since there does not exist the leading one at these positions, but you see the leading one is only which position? At first position, which denote the variable x1, and second row at position row number 2, column number row 3. So here here you see it denotes the position for variable x3, and in third row it denotes the position for x6. So what's about the remaining variable values? Since these variables position does not exist here, so we must suppose this variable as free variables. So the procedure is that we must suppose free variables equal to any unknown. Let's suppose x2 is a free variable, so we suppose it equal to r. And next unknown is x4, x3 equals. Next unknown is x4, so x4 equals to, we must suppose s. And x5 is also free variable, so we must suppose equal to t. So the methodology is we must suppose the values of the free variables equals to some unknowns, some unknown constants, that is x2 equal to r, x4 equal to s, x5 equal to t. So if you write that system, that augmented matrix or reduced echelon form of the matrix in matrix form, we may obtain the answer x1 equals to minus 3r minus 4s minus 2t, x2 equal to r, x3 equal to minus 2s, x4 equal to s, x5 equal to t, and x6 equals to 1 upon 3. minus 1 upon 3, 1 upon 3. So in that way, we may find the values of 6 variables. But you see, since the values of x2, x4 and x5 are infinite values, so if you plug in these infinite values here, in place of x1, in place of x3, in place of x5, we may obtain the infinite values. So therefore, we may say that solution is known as infinite many solutions.